Good evening, sir.
Hello, Pratham. Am I audible?
Yes, sir.
Okay, so you joined
I,
very late.
I have an exam on Sunday, so for preparation, I turned off my phone, so no
For
alarm.
preparation, you know, only like your class is for only 40 minutes, right? And it's already 24, so that's why I'm saying. See, okay. Should I start with the potential? Because in the last class I told I will be starting with the potential topic.
Yes,
Or because look, in the today's class, time is very less. Okay, so what do you think? Any doubt you want to solve? Any topic which you want to cover from the previous topics which we have discussed, or I should start with the next?
I think we can start with the next.
I can start with the next. So can I just share my screen with you? Check it. Um, I shared. You can just check this.
Yes,
Is it visible?
yes, sir, yes, sir.
Okay. Pratham. So today what I am going to start is it's lecture 10, I think. Lecture 10. Um, Electrostatic. Okay, wait, this I'll put the name after. So look, whatever we have covered is in the previous chapter. What we had is we had a single charge. Okay, due to this we were studying the effect of electric field, right?
Yes,
Electric field. Now here after what we do is if there is a charge, if there is a charge, okay, clear them out. If there's combination of if there is a combination of charges and there is force between them and a force between them, then there must be some energy associated with it. Must be some energy associated with it. Okay, so hereafter we are going to conclude the leave this. Let's put it like this. Okay, so what I'm going to do discuss first is I'll be having a charge. Okay, let's say I have a charge q, right? And I have another charge, let's say q naught at the infinity point. Okay, what my task is, I want to take this charge from here to this point q. Is that clear?
yes,
What my task is, I have a one charge at infinity. Okay, I want to take this charge. Okay, from here I can think this one. Okay, I have a charge q over here. I have another charge at this point. I want to take this charge from infinity to some close distance, let's say r, at some r distance here. Okay, this is what I want to do. I don't know is whether I need some energy to pull it here or what I have to. I'm not sure of it. Okay. Then how I should calculate? Any idea? Like what operations I should do? I know one thing that the force between these two charges, I know how to calculate. Is it fine?
yes,
But there's one problem in it. What I want to do is I want to take this charge from here to this point, right? This
yes.
is what I want to do. But if this charge is at infinity, what will be the force on this charge? K Q divided by infinity comes out as zero, right?
Yes.
So in this reason, I'm not sure what is the value of force, right? So
Hmm.
what kind of this electric field force is? It is a kind of conservative force, right?
Yes,
Conservative mean to say if you had if from going A to B you are doing W amount of work, then going from B to A you will need minus W amount of work. Is it
Yes.
okay? So I am like you might have got the idea that I don't know how to calculate from infinity to distance r, right? I don't have idea like how I should calculate the work energy. Work done from infinity to this point, let's say A point, okay? I don't know. This is I don't have idea because I don't have idea of the force at infinity. Is that clear?
Okay.
But I have another option also. What is that? I know I can calculate the work done on this charge from taking this charge from this point to infinity. This I know, right? From taking A to infinity. This is I know. Why I'm saying this? Because I know what is the force at this point. That is K Q small q divided by R. Is it fine?
Yes.
Okay. Now one more thing. What we have to calculate? We have to calculate the energy of this charge, okay? And or
Yes.
I can say the energy required to take a charge from infinity to certain point. Okay, this is what I want to calculate. But what I am calculating is energy required to take this charge from point to infinity. Is it fine? So
Yes.
whatever I am going to get at the last, I will do the negative of it. Is that clear?
Yes.
Okay, so let's calculate energy required to take this charge from A to infinity. Okay, this is what my task is. How I should do. I know one thing. What is the total energy? Energy is nothing but the work done, right? How much work I'm
Yes.
going to do. Okay. So, okay, energy of this charge will be nothing but how much work I am going to do in this object, right? So, what is
Yes.
work done? I know how
FF
much
first.
force I'm. Hello. Yeah. So look, let's discuss which force I am going to apply. You know one thing, I can apply any kind of force. Let's say that there's a force in between them, that is F. If I'm applying some
Okay.
other force, let's say, which is less than this force, so like I'm not able to move this. Is that clear?
Yes.
But so there should be the force at least equals to or greater than. Okay. So if it
Yes.
is equal, then in that case I will be able to move it. Okay. But
Yes.
if it is greater than, then what will happen? Let's say I'll just give an example. Okay, let's say this there's a force F in this direction, and I am putting a force F dash. If my F dash is greater than F, that then what is going to happen? F dash minus F will give some acceleration to this object. Understood?
Yes.
So what will happen if some acceleration is there? It will convert it into velocity. You can see initially charge don't have any velocity. If it will
Mm.
become velocity, if I'm giving some energy, so some of the part of it will convert it into potential energy and kinetic energy. Is that clear?
Yes.
So what I want to do is I want to avoid this kinetic energy. So what I should do? I wanted to avoid the effect of this acceleration. So what I should do?
Put it at infinity.
Your voice is a bit low.
Uh, can you hear me now, sir?
Yeah, now it's fine.
Put it at infinity.
To take it, look, I'm saying when I'm taking this charge from here to here, and if my force is greater than this, so what is happening? The energy, what I was providing to this guy, it is getting converted into kinetic energy part, right?
Yes.
But I don't want that effect because look, if you're going like this, there will be an effect of velocity, acceleration, all this. It will become a complicated equations for us. Okay, what we want to do, if you know what the chapter is potential, so my main focus is on the potential energy. Is that clear?
Yes.
So what I want to avoid kinetic. So how I can this how I can avoid this kinetic energy? What I can do is if I want to avoid kinetic energy, it means I have to avoid this velocity. Is it?
Yes.
If I had to avoid this velocity, means I have to avoid acceleration. How I can avoid acceleration? Making this whole equation to zero. When this is going to happen, it means my f dash should equals to zero. F, right? It means at every point the force and this force should equal to equals. Is that clear?
Yes.
Okay, so let's remove this. So when I'm at this point, what I will do, I will apply the force only equals to the force which is equals to in between. Okay, let's say this mode by here, then you know that force is nothing but k q divided by r square, mean to say r has changed. So there will be another force. It means now I will reduce my force or increase my force. Is that clear? So my force is also varying. I can say that.
Yes.
Okay. So what is my force value? Let's say this is force applying. Okay, work done by me. Let's write work done by me. So this is me, m. Okay, men basically. So what it is nothing but the force on the charge by men into how much distance he has moved. Is it the work done? Looks like.
Yes.
Okay, so what I have to do, I will try to integrate. Before that, let's put the value. What is the force? Force is nothing but k q smaller q divided by r square. Why I'm saying this? Because I have already proved that what look, if I don't prove it, I don't know what is the force I'm going to apply. But I have proved you what should be the magnitude of force, right? I just proved you that F should equals to F dash. F dash should equals to F, right? And F is nothing but k q by r, basically the force between charge. Is that clear?
Yes.
Okay. So let's say okay, no, not remove it. So m becomes k q q divided by r square. Is that clear?
Yes.
Okay, so I am going for x. This is your distance x. Let's say this is the distance. Okay, let's make it x. Clear? Now I am going from 0 to w. I am applying this much of energy maybe, and I am going from some distance x to infinity. Is that clear?
Yes.
So if you integrate this, you will be getting w equals to k q 1 by infinity minus 1 by x square. If you solve this out, what you are going to get k q by x square. Is that clear?
Yes.
And there is a negative also. So,
Yes.
okay, till now, any doubt you have?
No.
Okay, so I have calculated something that is a work done, right?
Yes.
So, what do you think? Is it the energy of the charge?
Yes, you said work done is equal to energy.
Work done is equals to energy, but this is the work done by me, right?
Yes.
So whatever the work I'm going to done, it is not the energy of the charge. Or I can
Okay.
say it is. What do you think?
Okay. So the work done is done by you, so it's not by the charge.
It's not by the charge. Okay.
So it's
One more thing.
negative.
Yeah. One more thing. In which direction I'm applying the force?
Negative.
Negative mean to say.
Like you.
Look, I was applying force in this direction, right? And
Yes.
displacement is this direction. So I can say this is zero. Like this is cos 0 degrees. So this
Haha.
equation is for now fine, right? So this is
Yes.
the work done by me. Basically the men. Any doubt here?
No.
So what do you think? Am I doing the negative work on this object?
No, it's
If you
positive.
It's positive, right? So
Yes.
why this equation comes out to be negative?
Because it's work done by you, not by
No,
the
that is
charge.
fine. But do you like okay? Why do you think it comes out to be negative? This is what my answer is. Look, the reason behind this is if you see, I have a positive charge Q here, and negative charge Q here, right? The both for positive charge. Is it?
Yes.
So what happens is there was an already an this kind of repulsion in between. Is it?
Yes.
So this, like due to these charges, this charge already wanted to go outside. Is that clear?
Okay.
So
Yes.
did I help him and by myself? No, right? I didn't help him because even if I don't help him, he could have leave the place.
Yes.
Understood the thing? It is similar to the thing that a truck is there. It is moving in this direction. What you did, you like let's say it is moving with 10 meter per second. What you did, you stand at the back and touch it. So did you done any work on this?
No.
No, right? What happens is even this truck worked on you, not you worked on it. This because if you just stick to the truck, what will happen? You will also move along with the truck. So work done by you on truck will be negative, and work done by truck on you will be positive. Is that clear?
Yes.
Now instead of this case, if I had a negative charge over here, let's say this is a negative charge, then what will happen? I had a Q, I had a this. there is an attraction in between, right? If you
Yes.
see, there's an attraction. Okay. If you see, if I put the negative in the equation, I could have got the positive. It means whatever the work I was going to do, that would have been positive. Is that clear?
Yes.
Okay. So how I can say this? If you see carefully, there's a foundation in between, right? And if you're taking this charge from here to here, it means you are breaking the foundation. Can I say this?
Yes.
And if you want to break the foundation of something, you need to provide energy. Is that clear?
Yes.
So in this way, did you understood the concept of this
Yeah.
negative
Yeah.
and positive thing in case of energy and all?
Yes.
Okay. So KQ minus KQ divided by R. All right. So I can say that work done in taking an object from infinity to some particular point, what it will be. Okay, look, whatever I have calculated right now, it is the work done of me in taking the object from here to infinity, is it?
Yes.
What I wanted to calculate, I wanted to calculate work done of me doing taking the object from infinity to a. So what it will be, k q by r square. Is that clear?
Yes.
Now, if you see carefully why this comes out to be positive, let's say I had a Q charge, a small Q charge. Let's say I don't had any Q charge. Here I had a charge. Here force was zero. Let's say if I take this positive charge to close to, let's say this is the point from there, you started feeling some force right in between them. Let's say here you came. When you try to pull it like this Q will try to push it, right?
Yes.
So you are doing some work against and force. In that case, you need to apply energy. Is that clear? Basically,
Yes, sir.
when you need to apply the energy, when you need to apply the energy,
Yes, sir.
right? When you need to apply the energy, when you have to do work against something, right? So here you are doing. Okay. Now, if I ask you, I took this object from here to here and I stopped it. So, what is the energy of this object?
I didn't understand. You took it there, then you stopped it.
Yeah, like I took it and at some point r I placed it. Okay, I stopped it here and I left it. Let's say I just took some thread and bound it. Okay, now just tell me, what is the total energy of this thing? Can you tell anything about this?
You mean positive or negative?
No, just the energy, whatever. What is the energy of this system, if I ask? It's a very simple, right? What is the total energy? Like, let's say, what is the work done? Work done, I know this is the work done, right? It
Yes.
is nothing but equals to the energy of the system. I can say change in kinetic energy plus change in potential energy, is it?
Yes.
If you see carefully, does the kinetic energy change in the whole path? Even I was taking the object, I was taking very slow, that velocity is not changing. I told you that time also
Yes.
when we started. So can I say this portion is going to be zero? So can I say the
Okay.
whole energy which I gave is converted into potential and energy of the system?
Yes. Yes.
Okay, so you can call it as a negative of, like, okay, you can call it as a change in potential energy equals to q by r square. Is that clear?
So, but you were saying that the charge is coming from infinity and you stopped it just before.
Stopped it before me to say? No, I am
Stop.
saying I took the charge from infinity and stopped it some nearby range. Okay, at some distance r.
Okay.
Okay, look.
Okay. Okay.
Okay, just take a minute and look at this point. Look, because here you have to be careful because there's too many things negative, positive, and related to energy. Okay, so you have to be clear with this so that in the further topics we don't have any doubt in this.
Okay.
Is it clear?
Give me a second.
Okay, you can take your time because look, today we can only do this part. Okay,
Okay.
and one more thing, next class, because you have only 40 minutes of your, I have only 40 minutes of your class, so be like join on the time. Okay.
Yeah. I will. There is an
Okay.
exam on Sunday, so that's why.
Okay. Okay.
There's an
That's
exam tomorrow also, so I have to
okay. That's
prepare.
so that's fine. You can prepare, but okay. If you are like not joining, you can just put the message. Okay, that's what I'm
Yeah.
saying. Okay.
Yes. Sorry, sir.
Okay. Is it clear?
Yes, sir.
Okay. So, I'll just keep it there. So this is what the formula for energy looks like, which we are going to use in this chapter.
Yes, sir.
Is that clear? Hmm. Okay. So this is what it is. It is the change in energy, change in the potential energy. Okay. Now, what we meant by the change in potential energy, I'll put highlight over that also. Change in potential energy is nothing but what I can say. What you can say about the change in potential energy? It is nothing but the final potential energy. Okay, point of the final potential energy. Who is it that minus this, minus initial? Is that clear?
Yes.
Okay. I can also say that this is nothing but let's say what I could have done. I had a charge at some this point, right? So what I could have done is I took the charge from here to here. Okay. Then I took the charge from here to here. Is that clear?
Yes.
So do you think in this path or directly taking like this? What do you think then? And there will be difference in energy if if I choose these two paths.
Uh, Work done is path independent, right?
Yeah, the main idea is work done is path independent. The reason behind this is the very simple reason behind this. What is that? The force which we are choosing right now. What is the nature of that force?
I don't know. In what sense?
A conservative nature, right?
Acha,
Not
yeah.
conservative, conservative. Like, what is
Yeah.
the reason? Like it is path dependent. The conservative nature. Okay,
Conservative.
it is not a path dependent thing. If the force is path dependent, then I can't say like by choosing different path, having the same final and initial point, I will be having the same what I can say same work done, the total work done. Okay, so this is
Yes.
only valid if your work, if your force is what, which kind of force you had,
Conservative.
it should be conservative force. Okay, so that's the thing about a very basic, the first thing of the this potential thing. Clear?
Yes.
Okay. So I'm going to at last I'm going to write one word. Okay, basically one thing that is your this change in potential is just nothing but the negative of work done. Okay,
Okay.
negative of work done by conservative force. Be clear what I'm writing. It is negative of work done by conservative force. Now let's get back to that equation. I told you this is the potential energy, is it?
Yes.
I equated it equals to what work done I did. Work done by men, right? If you could remember all the things which I derivated, it was the work done by men, right?
Yes.
Okay. So this is the work done by men. And I have equated it equals to delta U. But if you see at last, I have also equated it equals to work done negative of work done by conservative force, right?
Yes.
So what this means actually, just let's get back to the equation. When I had this charge Q, when I had this Q, okay. If you see, let's say both are positive. So in that case, I was taking this charge from here to here. Is it
Yes.
okay? Okay, let's make it positive so that it will feel better. Now, if you see, what is the direction of force? This is the force, direction of my force, right?
Yes.
But what is the direction of conservative force? This is the direction of conservative force, right?
Yes.
And I'm taking it from here to here. So if I say work done by me is nothing but the force multiplied by this object, the distance, right? Displacement.
Distance.
So you can see direction is same. So I can say it is coming out to be positive. That's fine for me. But
Yes.
what is the direction of this? If you see, distance
Negative.
is still the same, magnitude is still the same, but it is negative. So you can easily see that work done of men, like the person by us, will always less is negative of work done by conservative force. Clear?
Yes.
Okay, so whatever energy I am going to put on the charge, that will be the change in potential energy for the object. And then the work done by the negative, like work done by the conservative, should be negative of the change in energy, change in potential energy. Is that clear?
Okay. Yes, sir.
Okay, so whenever you find this equation delta U equals to minus W, it means this is change in energy, this is work done by conservative forces. I hope it is clear now.
Yes, sir.
Okay, let's take another case also. The last case after this, I'll end the session. If this would have been positive, then what could happen? If you see, I am going it this way, right?
I can't see the
No.
anything. Can you redraw?
wait, here I'm writing Q, Q, the infinite one, right? If this is the case, what is the direction of conservative force? You will say, okay, this is the direction, right? Basically, all the directions are there, but we will check only which direction we are moving.
Yes.
Okay, so if you see, this is the direction of conservative force, basically between these two, right?
Ye-
Okay, and I said I'm going from here to here when I started the first derivation. So in that case, I said, okay, I'm going in this direction. Is it?
Yes.
But that time I also told I will apply force such that what I can say, its velocity should not get increased. It means I was going to apply the force in this direction. Now makes sense.
So yes, yes.
Because what is going to
Uh,
happen? Look, this is a conservative force, right? If I also
yes.
apply the force in this direction, what will happen? Fc plus Fm will gives rise to velocity which I don't want. Even if I
So
remove my
wasn't the conservative force towards the Q charge?
no, no, this is a positive charge, right? Between two positive charges, there's a repulsive force, right? This will apply,
Oh,
this
yes, yes.
Q is going to apply this direction, this is going to apply this direction. So this is
Yes.
Fc. Okay, now I told I want to take this charge from here to here. Even if I don't apply any force, this charge can reach it by itself, is it?
Yes.
So if I'm applying force, does it make any sense?
No.
Making sense. Where it is making sense? It is destroying its energy. Okay, it is what when
It
I'm
should be
doing
in
something now,
opposite
it is
direction.
taking some part of an energy. How it is taking? Look, if you just don't apply, what will happen? The charge is there, it has some mass and acceleration. It may be like force is there, then acceleration will be there. If acceleration is there, velocity
Yes.
will be there. Velocity is kinetic energy there. But
Yes,
if I'm
yes.
applying opposite force, and I'm applying exact opposite equals to this, what I'm doing, I'm making net force equals to zero. It can just change its position. Okay, if in that
Yes.
case, it should very similar such that it can just change its position from here to here without changing its velocity. Is that clear?
Yes.
You can see where I am helping. I am helping it to not increase its kinetic energy, right? So now, if you check about the work done, my work done will be negative. This is my work done direction. This is displacement. Total should come out to be negative. Let's say right now,
Okay.
man. Here you can write it as conservative. It is positive, and it should be positive because force by conservative in this direction, force by object is in the like okay direction. Displacement is this direction. 0 degrees should be positive. That's fine. Okay, now if you have to calculate the potential energy of object in this case, change in potential energy, it will be negative. Why? Because it should be negative of work WC, and WC is positive, so total will be negative. Is that clear?
Yes, yes.
Let's talk about the real effect of this also. Why it is negative? If you see carefully, what is your potential energy? It is nothing but the energy at the place at the final place minus initial, right? When you
Yes.
are at near the charge, you had some energy. Let's say you had some repulsion and something, right?
Yes.
But so if you want to stand here, you need such amount of energy. Is that clear?
Yes.
Okay, let's say that energy I'm calling Q. Let's W. But if you're going from here to infinity, do you need some amount of energy to stay here?
Two?
To stay here, let's say,
No,
do you
no.
need this much amount of energy to stay here?
No.
No, right? You're very far. So I can say you are, let's say, very W. Okay, let's say you have not infinity, let's say some here position. Okay, so you know W, final minus initial. This is lesser, this is
Yes.
greater. So it should come out to be negative. Got the idea?
Yes.
Okay, so this is the thing which we are going to cover in this chapter in a very detail, in a different terminologies. Okay,
Yes.
yeah. So that's all for the today's class. Okay. Um, okay, I don't have too much to send. Okay, which chapter you are having an exam?
Electric EC and EP, electric current and electric potential.
All right. So try to solve the problem based on that.
Yes. I
Okay.
am.
Yeah. Any doubt?
No, sir.
Okay. So you can just leave the session. If you
Okay. Bye, sir.
good then.